Hey, welcome to our second video for Unit 0. Let's get right into this one. So on this page, we're looking at different types of lab equipment that can be used to measure volume. So we've got a graduated cylinder, a pipette, a burette, and a volumetric flask. So you can kind of tell that each of these have a different amount of precision in the amount that they can measure out. So based off of that, you're going to know a certain number of digits from whatever it is that you're using. So of course, this burette is going to be a little bit more precise than the graduated cylinder. The pipette and the volumetric flask, they are pretty precise to one point though. So what we're going to find out is that we're going to have a certain number of certain digits, and there's going to be one uncertain digit. Like for example, usually in the burettes, they go down to 0.1 milliliters. So you're going to have the hundredths. So it'd be like 0.1 something, like 0.15 or 0.16. That the 5 or the 6 would be the uncertain digit. So whenever you're recording your volume, you're going to have that one uncertain digit. So that's going to be really important. And I'm going to teach you a little bit more about that whenever we do this in lab. Okay, so significant figures include all those certain digits as well as one uncertain digit. And we assume that that uncertain digit is within plus or minus 1. So looking at significant figures, all non-zero integers are significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all of those, anytime you see them, always significant. Zeros are where it gets tricky. So you can have a leading zero, a captive zero, or a trailing zero. All of those, it just depends, okay, for zeros. If you have an exact number, which sometimes you're given an exact number for a problem, those are assumed to have an infinite number of significant figures. Okay, so looking at the zeros, basically, if you have leading zeros, they are not significant. They're going to be zeros that are to the left of any non-zero digits. So in this case, we have 0.0025. All of these zeros are to the left of the first non-zero digit, the 2. So they are not considered to be significant. So as a result, 0.0025 is only considered to have 2 significant figures. Captive zeros are always significant. Basically, they're trapped between 2 non-zeros, so in this case, the 1 and the 8. So 1.008, where these zeros are captive and considered to be significant, has a total of 4 significant figures. Trailing zeros depend. So if there is a decimal point, they are going to be significant. So in this case, 1.00 times 10 to the second. Since we have a decimal point, these zeros that are trailing, okay, they're to the right, are considered to be significant. However, over here with 100, since there is no decimal point here, these zeros are considered to not be significant. So as a result, only this one is significant, and 100 without the decimal point has only one significant figure. So what matters here is the decimal point. If there is one, those trailing zeros are going to be significant. If there is none, those trailing zeros are not significant. Even though this number is 100, it only has one significant figure. All right, exponential notation, aka scientific notation, is something that we are going to use extensively, and it really just helps for writing a number that has just a lot of digits out in a way where it's just a little bit easier. Okay, so in this case, we got 0.000060, and that's a lot of non-significant zeros. So why not write it as 6.0 times 10 to the negative 5? Basically, how we did that, we moved that decimal point 1, 2, 3, 4, 5 times to the right. As a result, since we're moving to the right, it's negative, and we moved it 5 times. So that's where 10 to the negative 5 came from. What's also really important here is keeping with the same number of significant figures. So since we had 2 here, we need to make sure that we also have 2 here. So 6.0 has 2. That decimal point is really important here. It is the same number of significant figures as we had here. All right, take some time to figure out how many significant figures are in each of these problems. Finally, we are going to look at some mathematical operations. First, multiplication and division. These both work the same way. The example that I have here is multiplication. So we're multiplying 4.56 times 1.4, and we end up getting 6.38. But the question is that the right amount of significant figures? Well, for multiplication or division, we're going to look for the number that has the least number of significant figures. In this case, it is the 1.4. There are only 2 here, whereas there are 3 here. Since there are 2 here, that means that our answer needs to also have 2 significant figures. So 6.38 has too many. We need to round to only have 2 significant figures. Since this is an 8, we're going to round up. That gives us 6.4. Next, we got addition or subtraction. Again, these work the same way, addition or subtraction. Basically, what we're looking for is the least number of decimal points. And we're adding 12.11 to 18.0 to 1.013. Adding all of them up, we get 31.123. Is that the correct number of significant figures? It is not, okay? Because the least number of decimal points that we have is in 18.8. 18.0. So we need to round to the tenths because that is where our last significant figure is here. So we're going to round here. This is a 2. We're going to round down. That gives us 31.1. Okay. So the decimal point, the 1 decimal place here mimics the one with the least that we have in the problem. Anytime you have a series of calculations, wait until the very end to do any rounding for significant figures, okay? Don't do it at every step. That's gonna take way too much time. Wait until the end to do it. Okay, now at this point, go ahead and do some more practice. So go ahead and do this one, this one, this one, this one, and this one. All of the answers are in the notes on the PowerPoint presentation that I've given you. And that's it for today.